The seismograph was developed in 1855 to record the shock waves produced by earthquakes. As shown in this diagram, it consists of two metal frames firmly anchored in a bedrock. A seismograph machine. A heavy weight is freely suspended from one of these frames by a spring. When an earth tremor shakes the support, the flexible spring keeps the bedrock motions from reaching the suspended weight. The weight, therefore, tends to hold its original position, despite the presence of earth tremors. A seismograph machine. A simplified diagram of a seismograph, which is used to draw records of earthquake tremors. The rotating drum on the left moves up and down when the ground shakes, but the weight on the right is isolated from the earth tremors by its supporting spring. Attached to the stationary weight is a pen which traces out the motion of the drum. The other frame supports a rotating drum covered with graph paper, as shown in the sketch. Because the drum is rigidly connected to the bedrock, it faithfully follows the movements caused by the earthquake. A pen mounted on the stationary weight then traces the movements of the drum on the unfurling graph paper, thus providing an accurate measure of the earthquake's force. One of the first uses of this new instrument was the observation that an earthquake's shock is transmitted around the world in several different forms. The slowest is called a surface wave, which moves like an ocean wave along the Earth's thin, curved crust. Other waves, whose existence was unsuspected before seismographs revealed them, move straight into the Earth at substantially higher speeds than the surface wave. These speedy waves are of two kinds: primary or P waves and secondary or S waves. P waves are the faster and more penetrating of the two, moving easily through the Earth's dense interior. The slower S waves have a transverse motion like that of a plucked guitar string. S waves travel well enough through solids, but die out rapidly when they enter liquids or gases. At a seismograph station, the first notice of a distant earthquake is given by the arrival of a train of P waves, the fastest ones. Later the S waves arrive. The interval between the two depends on the distance from the focus of the earthquake to the station. Still later the slowest waves, the surface waves, arrive, journeying along the thin, curved medium of the Earth's crust. Pinpointing an earthquake's place of origin, or epicenter, is done by 3 or more seismic stations in different cities. Each station determines the time interval between the arrival of the fast P waves and the slower S waves. From these data, estimates are made of the distances the waves traveled. 3 circles are then drawn on a map, with the 3 distances as radii. At their intersection is the epicenter of the earthquake. By analyzing data from seismographs, geophysicists are able to deduce a great deal of information about the Earth. When a powerful earthquake occurs, a complete set of shock wave travel times is obtained from the seismological observatories that dot the Earth. From these it is possible to infer the speeds of P and S waves at various depths in the Earth. We know, for example, that these speeds tend to increase gradually as the waves approach the center of the Earth. Also, there are several depths at which sudden shifts in the speed of travel occur. Scientists know that such shifts must signify radical changes in the properties of the Earth's matter at such level. The boundaries that these levels mark between layers of different kinds of material are called discontinuity. The topmost discontinuity is called the Mohorovičić discontinuity, after its discoverer. Above this discontinuity only the crust of the Earth, a thin shell of rock about 3 miles thick under the ocean floors, but with an average thickness of about 20 miles under the continents. Above the Mohorovičić discontinuity, the P and S waves travel at 4.3 and 24 miles per second, respectively. Below it they travel at 5.0 and 2.9 miles per second. Their speed then increases steadily for the next 1,300 miles downward, reaching 8.5 and 4.5 miles per second respectively. At the 1,800-mile depth, the speed of the P wave suddenly drops to 5 miles per second and its direction of travel changes abruptly, while the S waves disappear entirely. Evidently, there is a discontinuity at this 1,800-mile boundary between the Earth's mantle of rock and its core. Scientists believe that the region of the Earth below 1,800 miles is made up of molten iron, perhaps mixed with some nickel and cobalt. First of all, the core must be very dense to account for the Earth's great weight. And iron is the only heavy element that exists abundantly throughout the universe. Moreover, at the estimated pressures and temperatures of the core, iron would be a molten liquid. The Earth's core must be liquid because the earthquake's waves cannot pass through it. Their transverse vibrations can only pass through solids. Finally, the existence of the Earth's magnetic field can most readily be understood in terms of an electric current generated in a mass of liquid metal. Some geophysicists believe there is also an inner core some 800 miles from the center of the Earth. This discontinuity might be a transition to a slightly different alloy of iron and nickel, or perhaps a change in state from liquid to solid. All this movement causes quakes.